To talk a bit about this lovely paper out of the Tarpit. I really got into this paper because of Haskell project actually, called Project M36, and on the Functional TO meetup we talked about this, and that's when Dan mentioned, oh, you should come to Papers We Love and talk about the paper, right, not the implementation. So yeah, and here we are. So I added the cheeky subtitle, how we desperately try to avoid syncing. So it might seem as a bit of cynicism on my part. Sometimes I just get like desperate with like the current state of software, but I just wanted to make a caveat here. It's not cynicism on the state of the art or the state of the tools that we have at our disposal. I think William Gibson said that the future is here, it's only not evenly distributed, right? So I think that if developers do like a better job, and of course if the companies and ecosystems allow like this development job to flourish, like we can have much higher quality software and avoid several of the pitfalls that are pointed out in this so-called software crisis. But I digress. By the way, if anyone wants to ask any question, feel free to interrupt me. And yeah, let's get started. So, sorry. Okay, no silver bullet. So this is how the story of this paper starts. It's sort of a follow-up on another paper, which many of you might be familiar, called No Silver Bullet by Frederick Brooks. So it was a really widely discussed paper. Who here is familiar with the No Silver Bullet paper? A show of hands, please. Okay. Yeah. So the idea here is that we separate. So Fred Brooks in the paper separate the complexities. He starts talking about this software crisis, right? That comes from, I don't know, the 70s or something. And it's basically this idea that how come in the hardware world you have these like huge gains in productivity and the machines become exponentially powerful, and we don't see this kind of improvement in our development toolset. And I think people were basically astonished with the cost of software projects and how frequently these software projects got to a state where they were like technically bankrupt, to use the tech debt metaphor, right? So there was this perception that software is something that is very tricky and we are failing at it. And Brooks points something that I love. He basically says that it's not that software development evolves at a slow pace, it's that hardware evolves at a very fast pace, right? And it might seem conformist, but I think that what he tries to point out is that there is some discrepancy in the expectations of the industry. And I think that this sometimes has nothing to do with developers. Sometimes this has to do with like the whole corporate culture around software, right? There is a recent book in parenting, right, that talks about like the carpenter versus gardener as a parent, right? And basically uses this metaphor to show how the carpenter starts with like a fixed project and gets to like a very concrete deliverable artifact, whereas the gardener creates an environment that needs to be nurtured, and in that environment, like the vegetables will flourish. But of course, in that model of work, there is room for high complexity. Like it would be like chaotic behavior, right? Using the terminology of chaos theory, right? So very difficult to predict and very propense to like sudden starts of like exponential changes, right? Anyway, I digress. But the point is, I feel that even after the whole agile movement, the carpenter mindset still permeates the industry in so many levels. And I feel that this is one of the aspects that the paper No Silver Bullet was talking about, even if it's not using the exact terminology that I'm using now, but that's the idea. We have a misconception on the expectation, and we should be designing software differently than we are designing these physical, concrete artifacts, right? Because, anyway, let's go on. So the paper that I'm going to talk about is not the No Silver Bullet, right? It's out of the Tarpit, and it's a sort of a follow-up. So even in the abstract, it mentions, and it basically, the authors, they basically say, we disagree with that idea that most of the complexity that remains in software is essential, because that was the point in No Silver Bullet, right? That a lot of the complexity left in software development was essential. Therefore, we wouldn't see great improvements there, right? And in Out of the Tarpit, they say, we don't think so. We think that there's a lot of accidental complexity that is not essential to the problem itself. It's just complexity that arises from how we develop software. And then they go to define accidental versus essential. I'm going to get back there, but first, I think one of the main points that Out of the Tarpit tries to get across, it starts with a sort of motivational part about complexity, right? And they talk about testing and how there are different ways to understand the system. And this is super relevant. I think that if we read this paper today, although the paper was written in the 80s, right? It's still really, really relevant, because there is still a lot of this idea, the hope for the silver bullet, the idea that you can test everything, or you can formally define everything, and you can get away with really complex pieces of code because you don't need to touch that stuff, right? And I think that the first part of Out of the Tarpit tries to dispel this idea, tries to say, we need simple systems regardless of the tools available. Like, we need, like, simplicity and elegance are not optional, right? And it's also making the point that simplicity is hard, right? And it uses an amazing quote that I love. The quote that is in the paper, is not any of these. And the quote is, I conclude that there are two ways of constructing software design. One way is to make so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. The first way is therefore much harder, right? And I just put additional quotes that echo this idea, but not from the software development perspective. So these two are, like, this is a philosopher, right? He's talking about writing letters. And he says that the present letter is a very long one, simply because I had no leisure to make it shorter, right? And this is a Brazilian poet, and it says that it's necessary to write a poem several times, so it seems to have been written for the first time, right? And I see a lot of congruency between, like, writers, right, and philosophy, and what we do with software development. And of course, like, mathematics also has this concept of elegance that is very, very intrinsic to mathematics. Not so much in engineering, though. Hence, I think that sometimes we get into these misconceptions of, anyway, but I'll digress again, so I'll avoid rants, right? And let's just say that informal reasoning, back to Out of the Tarpit, so they make this case that informal reasoning is very important. And one of the reasons, the argument that they use is, regardless of what you're doing, if you're writing tests, you need some sort of informal understanding of what you're testing, right? If you are doing a formal specification, you probably will also start from informal understanding of what are these requirements. To read code, the same. So we always need to keep a mental model. And it's funny because it's something that I don't think was known to neuroscience when the paper was written, but there are several experiments that support this evidence that our maximum working memory load is between 4 and 5 things at the same time. So before you access some like neural pathways that go to short-term memory, right? Your cache in your prefrontal cortex, it's very, very limited, right? And that's why in mathematics and in writing and in software development, using like as few concepts in one point becomes so important, right? Because it makes it much, much easier to remain with everything in our like working memory. Anyway, so complexity, this is the Goya Saturn, right? I have a very low tolerance to complexity. So I always feel that it's like Saturn, that it feeds on its sons, right? On its offspring. And basically the idea is that complexity feeds on time and generates more complexity. And in the paper out of the Tarpit, they also mentioned is that complexity compounds. So that is another problem, right? Because reducing our ability to understand the system reduces our ability to reuse parts that are already there and to properly fit into interfaces. So we end up like duplicating logic, or we end up like misusing abstractions or creating unnecessary abstractions. So all of these problems, they are secondary effects that compound on complexity. Although the out of the Tarpit also makes these states that all problems discussed by No Silver Bullet could be reduced to complexity. So this is the main problem, is all complexity. And to that remark, I'm not sure how much I agree with that. Although Brooks talks about changeability, right, which is definitely a sort of complexity, because changeability, if you think about it, it's like you add the dimension of time in your code, right? So it's still code, it's still complexity. You just have to understand how your code evolves through time, right? So that is definitely some sort of complexity. But Brooks also talks about conformity, right? Which is to conform to unnecessary complexity in the external world, right? Processes that are ill-defined or ill-understood by its users. And here is a point that might be a bit contentious, right? Because in Out of the Tarpit, they define essential as anything that comes from the user, right? So anyway, I'm nitpicking here on this definition of complexity, but let's proceed. So the paper starts talking about this, about like motivating the seek for elegance and for simplicity. It talks about how hard it is to understand these complex systems and how this affects. And then it goes on to talk about state. Then the idea is, okay, now that we know and we sort of agree that complexity is one of the main problems, let's attack complexity and try to unpack that, right? What generates complexity? And then it goes on to talk about mostly control and state, although it has like some other like secondary things, but I think that mostly it's about control and state. And especially like state, I feel it's like throughout the whole paper, right? So the main focus is definitely complexity arising from state. And this deeply resonated with me when I was reading, because even before reading this, I would always mention that like, oh, state is the root of all evil, right? And I think that one of the turning points in my life as a developer is when I understood that, oh, you can encapsulate state, actually not state, but you can encapsulate side effects into the type system, right? So when I started to get more familiar with Haskell and I started to understand the rationale behind the IO type, I started, oh, this makes so much sense, right? Because, anyway, I digress again. Back to the paper. I like this. This is one excerpt of the text where it says that one of the issues that affects both testing and reasoning, right, is that the exponential rate at which the number of possible states grows. For every single bit that we add, we double the total number of possible states. And everyone here, when it's testing, like on any testing framework, has come to that point where, oh, I have a branch in my logic, so I double the cases that I need to test. If I have a second branch, right, I double that number that was already doubled. So if you have a lot of branching complexity in your code, like, and I want to generate an exhaustive list of examples, this becomes impossible very, very quickly. Very soon we just, okay, I cannot write concrete tests for all possible scenarios anymore. Yeah, and if we think about it, this is true for every single bit of state that we add. Hence, a lot of what the paper talks about from that point on is managing state, right? So this is still the first, we are still discussing like the first half of the paper where they are still exposing the problem, right? Sort of talking, okay, what problem are we talking about? So it actually goes through existing approaches and says, well, this is what is out there in the world to deal with this problem. And then it talks a bit about object orientation, right? And there is a very, very interesting aspect of the identity and state, right? Because it basically mentions, and this is one thing that always haunted me as a developer, right? Why do objects that have exactly the same properties are not equal? Why do we have to define equality? And why there is a concept such as value object, right? Value object is precisely when I have objects in which the identity is defined only by its attributes. And in the paper, they actually say that this problem arises from the fact that object defines this entity that mutates over time, right? So even if they are the same in one point in time, they are not the same entity and they might be different tomorrow, right? And of course, if you go to like books about object orientation, there is a whole discussion around these on like what is an entity and what is a value object, but we won't get there. But it was just like something that hit me when I was reading this. Of course, right? The thing with state is that it brings like this whole issue of identity, and it becomes complex because you start to, sometimes it can become very hard to understand like when one thing is the same as another thing, right? And as a direct consequence, it also becomes hard to understand when one thing belongs to a certain set or not. But anyway, it also talks about the control flow. So it's not only about state, it's also, in the paper they also mention that, well, object orientation still has this problem because it basically tries to split the state into these objects, but the state is still there, it still has to be managed by the developer. And it also uses mostly a sequential control flow, right? So in object-oriented languages, you are still in an imperative land, right? So you still have to deal with, you have the implicit sequence, right? One line will be executed necessarily after another. Now, in functional languages, and the paper actually mentions Haskell, right, as an example of not ideal, but pure functional language. And it tells us about how this will avoid mutable state. And I just mentioned here, at least in some implementations, right, because of course Haskell is not the only example that we have of functional programming languages. And several languages that we consider functional probably will still have to deal with mutable state. But in Haskell, we don't, because...
Well, in functional style, you try to avoid state changes that are observable from outside of a function call.
Yeah.
So, sorry about that. Yeah. So in Haskell, you have the what do we call it? The state type,
Yeah, yeah.
and or stref type. Sorry, stref
Exactly.
type. That encapsulates the idea that you can mutate state as long as you do it inside of the stref action, and then that you run that mutation, and the runtime takes care of it for you.
Right. Yeah, because you have like the runtime that will manage all the actions inside the monad, right? Yeah, but this is at least is transparent to the developer, right? You can do things that the mutation is completely like controlled. So some benefits exist in the functional land from a more abstract control flow. So the control flow doesn't disappear, but in these languages we usually have slightly higher level constructs. So there is an attempt to use more like maps and folds as an abstraction for iteration. There are concepts such as like fusing of functions, where like in compile time you completely like eliminate some loops. So it's not that we don't have a control flow here, but it's a bit more manageable. And the logic, I didn't know anything about logic programming when I started reading this paper. I just knew that, oh yeah, Prolog exists, right? But the paper is very, very skeptic of the logic implementations. It basically says that current implementations of Prolog and OS, they have mutable states, they have problems with flow. Basically, it's a mess, like you don't get any benefits that were always like touted as, oh, this is the motivation to move to logical. So apparently the implementation sort of defeated that purpose. Okay, now this is interesting. Although it's what I already mentioned about the identity, right? And it's basically that the idea of the Theseus ship, right? That it's a Greek story of the ship that when travels, like people will always like change bits of the ship, and when the ship arrives at the destination, like all individual pieces are different, right? And then the question is this ship the same one that left, right? And for me, this is a very good analogy for this problem of identity, or how do we understand the way that the world mutates, right? Are these entities really changing, or each slice of time is an immutable entity? Because I think that's also one thing with functional, right? You can say that each difference in state is actually a different parameter inside your function call, right? So if you get the execution steps and you just slice them in time, you consider everything immutable. Anyway, but there's another thing that I want to talk here about, also about the identity. And for me, it's one thing that in Haskell becomes really clear, how values are not variables, right? And this distinction is lost in several programming languages, precisely because we use variables and values interchangeably, right? So there is an implicit deferencing operation that brings the value, and we end up creating these situations where, well, you have a variable that is not exactly the same as the other variable, although their value is the same. And this creates, I think, a lot of confusion in our heads when we are developing software. But anyway, the paper doesn't explore like this part of value and variable. This is just something that I was thinking about. And then there is this discussion about essential versus accidental complexity. Therefore, it also talks about how essential or accidental is data. And what they define as essential is everything that comes directly from the user, So if your user inputs data, right, that data is essential. And if your user reads some output, the logic that generated that output is essential, right? Now, if you use, I don't know, database sharding, right, to deliver that thing, your user doesn't even know what a database is, let alone sharding, right? These things, they cannot be in any way essential, right? Because these are implementation concerns and therefore should be treated as like accidental state and accidental complexity. And this is one of the main points of the paper. It basically says that we spend so much time with these accidental states and these accidental logics, right? If we could reduce this, like we could see dramatic improvements and we could focus more on what is essential, right? And this reminds me a lot about in object orientation when we talk about like a hexagonal architecture or onion architecture. So you have those like layers. In the functional land, we have this idea of having like free monads and different interpreters, right? So for me, all these ideas, they sort of try to tackle this separation of concerns of what speaks on the domain of the problem and what speaks in other correlated domains. Does anyone want to add something?
Design patterns in object-oriented programming, right?
Design patterns, exactly. You mean to model
The essential complexity.
the essential complexity? Not necessarily though, because you have several design patterns that are about implementation. Like if you have like a command pattern, right? The user doesn't really care how they are going to undo a command, right? So design patterns, I would say, yeah, some of them are probably related to or maybe they're just more abstract, right? Because you can use some design patterns in the domain part, but not necessarily. Well, so this table, which I also took exactly as is from the paper, basically shows that we have here several combinations of what is the data essentiality. So data essentiality is basically that criteria of whatever comes from the user is essential, right? So if you have like a data that is essential, it is coming from the user, and this is input, we can consider it essential state. Basically, this is what we have to be concerned with. Everything else is accidental and can be treated, if not eliminated, can at least be treated as a completely different thing and can be separated and put it in its cage so that if anything happens, we can completely re-implement that. And well, we will get there, but the idea is, for instance, sometimes we have essential data that is not input, it's actually derived, right? And but it's immutable, right? So this is very common, for instance, when you have all sorts of caching strategy, right? So you have some data that the user input, and then you want to create like an aggregate, right? But you want a cache of that aggregate. You want, like, I don't know, the sum of the total of orders, right? And you have some reports where you can't calculate it with a live query, and you just create I don't know, like a materialized view. Anyway, I'm just going now deep into implementation, but the idea is I can just create these cache states, right? That they are immutable in the sense that I will never change them directly. I can change them in the sense of, oh, I want to regenerate this from the source data, right? But you will never go to that sum and actually mutate that data, right? So this is still essential data, right? It's still data that is directly derived from the user, and it's still used in outputs, in reports, or whatnot. But it's being derived, and it's immutable, and it's easy for us to tackle in different ways and separate from our essential logic. This is considered accidental state, right? There is another kind of essential data that is also derived, but this is mutable. And someone might think, oh, but how come, right? If it's mutable, this becomes like something else entirely. So the caveat with the third row is that it has to have an inverse function, right? So if I, let's say, have items with quantities and units of measure, right? Let's say that if I change the unit of measure, I want the system to recalculate the units, right? And I want to store that new state. So I'm actually mutating the quantity, but I'm mutating with essential data because it comes from the user. The user is asking us to change that unit of measure, right? But this is not accidental state because I can easily go back. I have an inverse function, and if I just want to go back to my original state, I just need to revert that call, right? I just need to, instead of multiply, I divide, and then I go back to the original state, right? Sort of. Not clear.
It still kind of feels derived, like.
It is.
Yeah.
It is derived, but it's something that it is interacting directly with the user. That's why it is considered like essential data, right? But you're right. You could reconstruct that from the raw input. So it is accidental state, right? But sometimes you won't be able to completely get rid of this stuff, right? So yeah, it is derived, but it is mutable, right? So it's not entirely accidental, right? It's something that is being calculated from the user input. Now, the accidental data is more like something that is created completely out of an implementation need. For instance, if you have like a sharding table, right? Like a table that distributes hashes of customers over several servers, right? That thing is not created from any user data, right? It's basically on how we structure our storage, and therefore that is completely accidental, right?
Like the running total when you're looping over a list, adding up all the numbers, the current running total, that's it.
Exactly, the current running total, right? So also these intermediary states that we use, right? When we are like accumulating something, right? And these things are also considered accidental state, right? But they are not even like essential in terms of data. So of course, these are much easier to get rid of with tooling, right? So you can basically make your infrastructure take care of that stuff for you, right? Just like before we had like a variable with the counter when we are doing like a for loop in C, right? But then we come to like Python and you do just iterate over this collection and you got rid of that variable that captured your index, right? So this is the sort of like very easy elimination of accidental state. Okay, so when they talk about these different sorts of states and different sorts of logic, they also propose different languages to accomplish different goals. Or if not different languages, at least like separate parts of the infrastructure. So you would have something to deal with the accidental parts of the state. You will have something to deal with the essential state, right? So the idea is, let's try to break down this problem and handle with different tools. It's related to this idea of DSLs that is like, I think lately there has been like a huge revival on this idea, right? And the separation allows us to restrict the power of these different components, right? And the paper also mentions this idea that power corrupts, right? So if we have things that are too expressive, right, we tend to shoot ourselves in the foot, right? And of course, sometimes it doesn't make sense to have control in a language to specify state, for instance. Anyway, we'll get back to that. So now this is already the second half of the paper, and it's already talking about this proposed framework how we handle all this stuff. So we have that complexity, we have the state, which is a huge factor, and now we separate state into different kinds of state. How we handle this? So there is like a recommended set of components in the paper, and they basically have these. This is like the main diagram. So you have your essential state, which is that part where we saw in the table, right? That there is no derived data, right? So this is the raw user input. And their idea is that this would be like the base of the definition of the system. So you basically define the system around this raw input, right? And of course, they will talk about relational algebra to use and to manipulate this stuff, but we'll get to that later. And there are other two big components. The essential logic that will will point to the essential state, right? And this is a data dependency arrow. So if I change my essential state, I might have to change my essential logic, right? Because I'm basically changing the core concepts that I use to model the world. But I can change the essential logic at will, right? Without touching the essential state, because this is defined in a completely independent way, right?
So does that mean that you would separate these into modules in your programming language?
Yeah, sort of. Of course, the ways to implement this will vary like wildly, right? So you could say that your essential state is in one database schema. Let's say if you are using something like a PostgreSQL. If you're using like a project M36, you can say that you have also a namespace with a set of rel vars that are your essential state. But if you don't have an external database system, you can also say, yeah, I have this module, right? I have this specific namespace that defines my essential state, right? And I feel that this can also compose with other techniques to break down problems. So I feel that if we would talk about DDD here, like we would probably see that a lot of the concepts that are used in domain-driven design are actually in here in the essential state bar. But anyway, I'm not going to model this too much because I personally haven't given much thought to that. It just strikes me as something similar. Anyway, so yeah, there is this separation, and this could be a separate module or could be in a separate system. But what is important is that they are independent. There is a clear interface, and the dependency has only one direction, right? So if you change this, you have to change that, not the other way around. And all accidental state and control will refer both to essential logic and essential state. So if you change the essential state, you also might have to change accidental state and control, right? Not the other way around. Here we start to see how, at least in this ideal world that the authors are like talking about, how we could have like a very powerful separation of concerns and do most of our daily programming, right, in a world that is here around implementation, right, and we wouldn't have to change much of this, right, or also live in a universe where most of this is simply automated away, right, and then you have to deal mostly with this, and then these changes are extracted. Anyway, they actually don't get into this part of like how to implement, but they give some pointers, right? Which we will talk a bit in a minute. So they mentioned the relational model as a way to tackle the essential state. And here they really get into the solution part, the solution space. They mentioned that there are several benefits to the relational model. Data independence is mentioned as like one of the really, really strong points, because when a relational model was first proposed, they already had this idea of mapping a purely abstract model to a physical model of how the data is stored, right? So they basically say this is something good, is something that we should be using because the physical model is all accidental, right? And developers, we shouldn't be, right, really spending a lot of time figuring out that stuff, right? We should figure out the abstract model and use tools to automate most of the accidental part. Access path independence is also mentioned in the paper as one of the big benefits. And it's funny because I think the paper was written in a time when object orientation was still a shooting star, right? It was still ascending as a good practice. And they mention, it's disturbing how similar models to store data based on objects or on XML are similar to hierarchical databases that motivated the relational model. So it's very disturbing that all these people now are talking, oh, how modern it is to use an old database, right? When it was actually a step back in several ways, right? Anyway, I think that's not much of an issue today, but yeah, it's good to keep in mind that access path independence is great. The fact that I don't know if I need to first get a department to list the employees, or if I need to first get an employee, but to then list the departments, right? So this access independence, this power that the relational model offers, where I can simply describe what I want looks like this. You figure out how to give me that, right? Now this power is really spares us from much of the grunt work, and they mentioned this. The closed algebra that is provided as the relational algebra, all the results of the relational operators are relations itself, right? So basically you can, they are composable, right? I can get the result of any relational operation and feed into another relational operation, right? And I have a set of declarative rules for data integrity, right? So all of these points are pointed out as a reason for, this is why we believe that the relational model is the ideal candidate to store essential state. So back to that diagram, this thing here would be implemented as a relational model, right? And a set of constraints, of course. But yeah, mostly that stuff. And then they propose the FRP, which is not functional reactive programming. This FRP here is functional relational programming, right? Because their point is basically, okay, so we've shown all of this stuff. We show how relational model is great to manage that state. So let's mix these two ideas of let's mix those benefits that we have in functional programming languages, and let's use a relational language to deal with essential state, and let's create this hybrid, which we call functional relational architecture, right? The idea here is the essential state is basically a set of relations, rel-var definitions, right? Basically, we can interpret this as a bunch of create tables, right? So this is my essential state. The essential logic, or the behavior in business terms, right? We can implement mostly, or actually 100%. The paper, I think, goes on to say that this could implement all the business rules. Will be derive rel-var definitions. So here we already have some sort of accidental, actually still essential logic if it is derived, but it might have some accidental state in case of caching. Anyway, the idea is I can build my business rules using these derived rel-vars, which would be like views in a modern database system. User-defined functions, so of course in cases where I need some sort of control flow, I can use these user-defined functions. And integrity constraints. Then we have another component, which is the accidental state and control, right? And this would be basically the physical logical data mapping. So this is how the database or the system that you're using or whatever you're using will actually map this stuff into cache, different files, will shard, will do whatever is necessary to operate that data and to present to the users, right? And hints for performance. They are a bit dismissive here. I think it's funny because this is a very quick en passant topic on the paper. And I feel that this is like it's a can of worms, like that is gigantic. It's like, yeah, there is this little detail that we need to figure out, which is basically 50% of the life of a program, right?
We'll leave it as an exercise to the reader.
Yeah, yeah, exactly. We leave it. And yeah. And this is another point where I feel that the authors were a bit dismissive with the real world, because they use these, and I hate this naming that they use. They actually say other, right? So you have essential state, essential logic, accidental state and control, and all that nicely analyzed universe, and suddenly they say other. And other, I was astonished to find that is basically the way that the system interfaces with the world, right? Which is another point where I think that like most of our lives as developers, we spend actually here. So the other is a big part of this solution, and the authors don't explore this part very well, in my humble opinion. Anyway, the conclusion. Oh, and by the way, so the paper, by the end of the paper, they also give an idea of what infrastructure would be necessary to implement this stuff. And now we get back to that project M36 that I was talking in the beginning, right? Because the guy that created the project, he basically says, oh, this project is inspired by the paper out of the Tarpit, and my intention is to provide that infrastructure, right? So if you go to the part where they talk about the infrastructure for FRP system, it basically needs a set of requirements to implement all this stuff, right? And if anyone is curious about like how this could be implemented in Haskell, like you should check this project M36 on GitHub, because that is precisely what the author of that project has done. He has gone through like the list of requirements, implemented everything in Haskell, right? And basically say, okay, now this you can use to develop a full FRP system, right? Very interesting.
It's funny, this separation, because I can map each of these sections into, Elm, the programming language. So Elm that has each of these sections. So it has a model, which is the essential state. It has a view, an update, which is the essential logic, which is it manages state behind the scenes, that's the accidental state. And it has ports and commands, which are the feeders and observers.
I was thinking the same thing, because it's funny, it talks about FRP, right? And you immediately think of the functional reactive programming. And I was thinking exactly in these terms. I thought, wow, this sort of talks a lot to what people are talking about Elm, and therefore like React Redux, right? Which is sort of like inspired by Elm as well. So this idea, I mean, of course, it's not exactly as it was described in the paper, but you see how like these ideas were out there and they flourished in one way or another. And we might argue that it took some time, maybe 20 years, right? But yeah. So I would love to see, this is my conclusion, it's not the paper's conclusion. The paper's conclusion is very much like, yeah, we propose all this thing, we don't know if there is really a silver bullet, but there is a lot of work to be done. So here we leave to the reader, right? But my conclusion was, I would like to see a comparison of proposed architecture with some of its counterparts using a similar infrastructure, because they basically mention how these things could be implemented and how this would be much better than like an OO system or a purely functional system. But in any point in the paper, there is an actual comparison. Oh, look, this is the code, And by the way, they use some pseudocode to show how the FRP system is implemented. But they never actually show this would be the equivalent in object-oriented world. This would be the equivalent in a functional world. And I'm not so sure that their proposal, if we take like modern object orientation approaches and modern functional approaches, I'm not so sure. Like, how much are we gaining if we use a system as they describe, right? I will be curious to see this comparison. And of course, the comparison could be based on code length, coupling of components, and like other complexity metrics. And
Microservice architecture.
Microservice architecture, yeah. I would be curious to see this sort of stuff. I'm not saying that I will do, so don't expect anything on my repos. But just wanted to throw out there. I think it's something that was missing in the paper.
I think some of the stuff in the paper has caught on more than others. I'm surprised though that the relational, specifically like the relational programming part, hasn't had much traction as far as I've seen. Like, I've never worked with most of the programs I've worked with, when they do work in relational data, it's in the interest of getting as quickly out of the relational model as possible and into like whatever crappy data model they have internal to the application, whether that be objects or like badly nested maps, things like that. And so I'm curious if you know of examples of places that have taken relational things.
Yeah, I have the same frustration because my personal background is as like a database. I worked a lot with like the relational databases, especially PostgreSQL. And I was always a bit frustrated precisely with this state of affairs of like why people hate SQL so much. I mean, it's not the most beautiful thing out there, but you see some contradicting signs. Like people would say, oh, DSLs are awesome. I remember when Rails started, like back then, people would say, oh, you have these like beautiful blocks that you use to do something that is like a DSL. And then everybody was suddenly in love with this idea of DSLs. But SQL was terrible, right? And I don't know, maybe, well, anyway, let's not go there, but about examples of where this is used. So I thought the same thing for years, and then at some point I was like tired of these object relational mappers, and I thought, I think a lot of these problems have to do precisely with ORMs, with the idea of ORM, right? Because it's really, they are really two models that are very hard to fit together, right? And in the end, you end up shoehorning like one on another. And that's when I became involved with this project called Postgres that tried to map a SQL database to a REST service. Because HTTP actually is much more interesting to access relational data, right? Much more flexible than a class hierarchy, at least in my opinion.
Either of you familiar with Eve, our language being worked on by a fellow named Chris Granger? He did Light Table. You might have been familiar.
Yeah, Light Table.
So Eve is, at its core, I think it has a relational model. The data is always stored in a relational fashion, and you are always like. There is no sort of straight linear control flow. It works, well, a little bit like this, it sounds.
Cool.
So maybe something you would be interested in seeing.
Nice.
The closest I've seen is Datomic. Datomic doesn't do relational, like quote unquote relational algebra. They do a lot more like data lobby and tuple store types of things. But that's the idea is to have that in your application as well as at the data storage layer. But that's a little bit different.
Right. Yeah, and if someone wants to see like a very, very true to the relational idea implementation, I highly recommend the project M36. It's a really cool project, and they actually even have like a WebSockets interface. So you can actually run a server and send your like relational algebra expressions as a JSON. And then you send to the WebSocket and it comes back with like the data. Very, very cool stuff. That was it. I don't know if Any more questions, comments, remarks? Well, thank you all.
Let's hear it.